Physical science paper, exam paper 2015, question 2. Students use a motion detector to investigate the motion of a volleyball. The ball was dropped from rest and the results were recorded as shown in the graph below. So it goes up like that and then poof, down like that. What happens to the ball at the excuse me? What happens to the ball at the 0.40 seconds? Well, there's 0.40 seconds. So obviously the velocity is increasing as it goes towards the floor, and then all of a sudden it starts coming back up. The velocity increases in the opposite direction. So I'd reckon that's what happens to the ball at 0.4 seconds. The ball hit the floor and bounced. Show that the acceleration of the free-falling volleyball is approximately 8 meters per second squared. So we've got a velocity versus time graph. And to find the acceleration from a velocity versus time graph, you find the area under the graph. So we've got 2 points there. What have we got there? So the acceleration equals the rise over the run, which equals from 0 up to 3, well that's 3.1. Yep, that's right, over 1, 2, 3, 4. 0.4, 1, 2, 3, 4, yes. 1, 2, 3, yes, 0.4, which equals, come back to the calculator, 3.1 divided by 0.4 equals 7.75 meters per second squared down, which is close to our value there. Very good. Sketch a graph to show the general shape of the displacement against time for the volleyball over 45 seconds. Well, what's happening here is as this is going increasing its velocity as you're dropping the ball, so the ball is increasing its velocity as you're dropping it, so the displacement will also increase. It'll start off small and then get bigger and then get bigger until it hits the floor, and then the displacement will start coming back up a bit. So what that means is, remember that the displacement is, so it's going to be going up like that and then dropping back like that. So it will start off slow to about there, and then draw a line down there to indicate the point at which it bounces, and then it'll come back a bit like that because we're not actually measuring it all that far. It's a bit hard to tell what's going to happen. It's going to come back down there like that. So that will be displacement, and that will be time. And that will indeed be 0.4 seconds. What was the final displacement of the ball after 45 seconds? Well, coming back to our velocity time graph, not only can we find the acceleration from a velocity time graph while finding the slope, but we can also find the displacement. But we can find the acceleration, sorry, I'll say that again. We can find the acceleration of the velocity time graph by looking at the slope, but we can find the displacement by looking at the line under, the area under the graph, I should say. Again, I'm distracted. So, let me see. If I can, what I have to recall is that, in fact, the x axis is going along there. This is not the x-axis, this is -5. So we're looking at finding out what the area there is. And how far do we have to go? Find the final displacement of the ball after 0.45 seconds. So not only that, but it will bounce back up a little bit. So we have to take that bit into account as well. So what we have is the area under that is going to be, that is 3.1. Going 1, 2, 3, and that is going to be 0.4, and that area there is, we're just looking at this area here, we've come down because we've gone into the negative 0.5, so that's negative 0.3, say, and that in there is going to be from 0.4 to 0.5, so it's going to be 0.05, 0.05. So what we're looking at there is looking at this first area, displacement equals area under VT graph, which equals a half, because it's a triangle, multiplied by 3.1 by 0.4, I think it was, 3.1 by 0.4. 3.1 multiplied by 0.4 plus a half times minus 0.3 times 0.05 minus 0.3 times 0.05. Now, what we have is 0.5 times 3.1 times 0.4 plus 0.5 times negative 0.3 times 0.045, equals 0.6125. So let's go to the nearest centimetre and say 0.61 metres. Good. Now, the mass of a volleyball is 280 grams. Estimate the frictional force due to air resistance on the falling volleyball. Well, what we have here, if we're going to have a look at our volleyball, as it's falling, it's going to have a force due to gravity. And since it's a large thing, it's going to go down there. It's going to have force due to friction. So we're going to see this falling. The sum of these forces is going to be equal to what we observe this doing. It's falling at 7.75 meters per second down. So that is going to be equal to the mass. So following that, so the frictional force, or the sum of the forces, is equal to the force of gravity plus the force of friction. Now we know that the sum of the forces is equal to 0.280, because that is equal to 0.0280 kilograms, multiplied by 7.75, because that is the observed acceleration, and that's going to be down, equals force of gravity 0.280 multiplied by 9.81, because we know the acceleration due to gravity is that, it's going to be down, plus the force of friction. Estimate the frictional force, so we want to find out that one. So, bringing back this one, we're going to have 0.280 multiplied by 7.75 equals 2.17. 2.17 down equal to 0.280 multiplied by 9.81 equals 2.74 down plus F of friction. So that is going to be, if we subtract that from both sides, 2.7 down minus 2.74 down equals F of friction, Therefore, it's going to be equal to 2.17 minus 2.74 minus 5.7 negative down, or F of friction equals 0.57 newtons in an upward direction. A negative of that direction is the opposite. To make that into a positive, you turn it in the opposite direction. And that makes some sense. The friction is going to be going up like we said it was. Hooray! That's the end of question 2.